All right, let's take a deep dive, and I mean that literally, into something we do all day, every day, without even thinking about it. We're going to follow the amazing, totally invisible journey of a single breath, from the air all around us, right down to the tiny cells that are desperate for it.
Just think about that for a second. Over 20,000 breaths every single day. Each one is this incredibly complex, high-stakes event happening inside you. So what is actually going on in that split second you breathe in and out? Come on, let's trace the journey.
The secret behind this whole incredible process? It all boils down to a fundamental rule of physics, simple diffusion. You know, where molecules just naturally move from a crowded place to a less crowded place. Sounds simple, right? But your body has turned it into an absolute art form. Okay, our first stop is deep inside the lungs. This is the main event, what I like to call the Great Gas Exchange. This is the front line, where the air you just breathed in, the outside world, literally comes face to face with your bloodstream. Now, for this exchange to work smoothly, it's not a free-for-all. 4 things have to be absolutely perfect. You need something called a partial pressure gradient, which is really just a fancy way of saying you need more pressure on one side to push the gas to the other. Then you've got gas solubility, a super thin membrane for the gases to cross, and a huge surface area for it all to happen. It's a really delicate dance. And here's something that might surprise you. When it comes to this whole exchange, not all gases play by the same rules. Oxygen, the stuff we're dying to get, is actually less soluble in our blood than the carbon dioxide we're trying to get rid of. And we're not talking a small difference here. It's massive. Carbon dioxide is a whopping 20 to 25 times more soluble than oxygen. What that means is that CO2 can just leap out of your bloodstream and into your lungs like lightning. It's one of the key reasons our bodies are so good at taking out the trash, so to speak. So, the oxygen made the jump. It's in the blood. Now what? Well, it hops on the body's ultimate delivery service, the bloodstream. Think of it as a super highway for oxygen. But oxygen doesn't just, float around by itself. Oh no. An incredible 97% of it immediately hitches a ride on a special molecule called hemoglobin. This stuff is basically the dedicated taxi service for oxygen. Only a tiny little 3% actually dissolves straight into the blood. Let's just run the numbers to see how powerful this taxi service really is. So take a small amount of blood, just 100 milliliters. Inside, you've got about 15 grams of hemoglobin, and every single gram can carry 1.34 milliliters of oxygen. Put it all together, and that tiny bit of blood is hauling a full 20 milliliters of O2. That is one seriously packed vehicle. And here's where your body gets really smart. When you're just kicking back, relaxing, your tissues only need to grab about a quarter of that oxygen. But the second you start exercising, your body floors it, dropping off a massive 75% of the oxygen to those muscles that are screaming for it. It's a completely on-demand system. So that's how oxygen gets around. But what about the return trip for carbon dioxide? Well, that's a whole different ballgame. The huge majority of it, 70%, gets converted into something called bicarbonate for the trip back. About 23% does grab a ride on hemoglobin, but it sits in a different seat than oxygen. And the rest, about 7%, just dissolves in the plasma. So how in the world does that little hemoglobin taxi know where to make its drop-offs? This is the genius part. It's called the Bohr effect. See, in tissues that are working hard, they're producing tons of CO2, which makes things a little more acidic. That acid is the signal. It tells hemoglobin, hey, loosen your grip, drop the oxygen right here. It's a perfect delivery system. And the Haldane effect? That's just the other side of the coin. When that blood gets back to the lungs and suddenly it's flooded with fresh oxygen, that oxygen-rich air makes it really hard for hemoglobin to hold on to its CO2 passenger. So it gets kicked off, right into the lungs, ready for you to breathe it out. It's just a perfect system for pickup and drop-off. We've got the chemistry down, but who's conducting this whole orchestra? I mean, all of this is happening on autopilot. And that's thanks to some hidden control centers deep inside your brain. Tucked away in your brainstem is your respiratory rhythm center. Let's meet the team. The DRG, or dorsal respiratory group, handles your everyday chill breathing. When you need to ramp things up, like running for a bus, the VRG, or ventral respiratory group, kicks into gear for that forceful breathing. And the pneumotaxic center? It's the off switch. It tells you when to stop inhaling so you don't overdo it. So, what's the trigger? What tells these centers to get to work? You'd probably think it's a lack of oxygen, right? That makes sense, but it's not.
The main trigger is actually a buildup of carbon dioxide in your blood. Special little sensors in your brain and arteries detect this rise in CO2 and acid, and they send an urgent memo to the brain. It's time to breathe now. This whole system is amazingly tough, but it's not invincible. So what happens when this perfectly balanced process gets thrown out of whack?
Well, the system can get attacked in a bunch of different ways. With asthma, you've got inflammation from allergies constricting the airways. With bronchitis, it's usually a virus causing inflammation and a bunch of mucus. And then there's emphysema, which is just devastating. It's often caused by smoking, and it literally destroys the tiny air sacs you need to breathe. And of course, there are environmental dangers. For scuba divers, coming up to the surface too fast is a huge no-no. That rapid pressure change causes nitrogen that was dissolved in their blood to literally turn into bubbles. It's incredibly painful and dangerous. That's why a lot of pro divers now use helium-oxygen mixes. Helium just doesn't cause the same problem. And for so many people, the danger is in the air they breathe every day at work. Things like stone dust, asbestos fibers, cotton fibers, coal dust. Long-term exposure can cause scarring in the lungs that makes it harder and harder to breathe over time. It's a powerful reminder of why protective gear is so important. But maybe the most terrifying threat is the one you can't see, you can't smell, and you can't taste: carbon monoxide. The reason this gas is so deadly comes down to some really nasty chemistry. It binds to the exact same spot on hemoglobin as oxygen, but its grip is 200 to 250 times stronger. Once carbon monoxide latches on, it's not letting go. It forms this super stable bond and basically hijacks all the oxygen taxis. It completely shuts down your body's oxygen delivery service from the inside. You're suffocating, but on a cellular level. It's absolutely brutal. So, when you put it all together, from the simple physics of diffusion to the complex chemistry of blood, all the way to that autopilot system in your brain, this whole intricate, beautiful dance is happening inside you thousands of times a day. And the most incredible part? You don't have to think about it for a single second. It's a true biological masterpiece. But as we've seen, it's also incredibly delicate. So I'll leave you with this question. Knowing just how fragile this whole balance is, what's one choice you can make today to help protect